Okay, hi, this is Theodore Norvell. Um, because we've lost 2 more days to snow, I'm going to do a video lecture here, and it's going to be on finite automata. So when we come back, hopefully on Wednesday, we will, when we come back on Wednesday, we will carry on from where this video ends. So please watch the video all the way through before Wednesday. Okay, very quick recap. We were looking at regular expressions and regular languages. So we learned that there are 3 ways to make regular languages. Uh, so the empty set is a regular language. The set containing just the empty string, that is a string of length 0, the string of length 0, that's a regular language. And any set that contains just one string, just of length 1, that's a regular language too. Okay? So that's 3 ways of making simple regular languages. And then we had 3 ways of putting regular languages together to get new regular languages. And those were union. So if I have 2 languages I know are regular, then the union of those 2, and it has to be 2, it can't be an infinite number, that's a regular language. If I have 2, and again it has to be 2, regular languages, and I put them together by catenation, and catenation means that I take each string, here's catenation, M catenated with N, so the language M catenated with N is the language I can form by taking any string from M and any string from N. I'm going to catenate them together, and all the strings I can make like that are in the language M catenated with N. And again, it's important there's just 2. Now, of course, I could catenate together 3 by doing doing 2 and then catenating in the other one, right? That would catenate together 3, and I could do the same with any finite number. But catenation is limited to a finite sequence of languages. So there's only one way to get infinitely big regular languages, and that's to use Kleene closure. And Kleene closure, remember, is the Kleene closure of a set M being a language. So the Kleene closure of a language M is the set of all strings I can make by catenating together some finite number of strings, each of which comes from M. So I can take any sequence of strings in M and then catenate all of those together, and that gives me a string in M star. Okay? And then we had regular expressions. And a regular expression is a string that describes a regular language. So just as there are 6 ways to make a regular language, there are 6 ways to make a regular expression. Okay? We can make a regular expression that just describes the language, a language of length 1, a language that contains just one string of length 1. I have a regular expression which is the underlined epsilon. So that's as a string, that's the regular expression has length 1. It describes the regular language, which contains one string, which has length 0. And then we have the underlined empty set symbol, and again, that's the expression is a string of length 1. It just contains that empty set symbol, but the language it describes is the empty language. Okay? And then we have three ways of putting together regular expressions. We have alternation, which we represent with a vertical bar, catenation, which we represent with a semicolon, and Kleene star or Kleene closure, which we represent with a star. Okay? And we had all kinds of abbreviations, ways you can leave out parentheses, you can put in extra parentheses, and so on. But at heart, we just have these 6 ways of making regular expressions. And we had many abbreviations that are in common use. I won't use them very much, but a lot of these abbreviations you'll see in common use. Okay. So finite automata. Automata comes from 2 Greek words. Auto means self, like in automobile. As automobile is something that moves itself. And an automata, mata, is, well, mat is a rather rare Greek root. It apparently means to think or to will. And it's probably related to the word math, which is to learn. Mathematics is about willing yourself to learn, if you take the Greek root literally. Okay? Automata is something that thinks by itself or that has its own will. You also see MAT. MAT words in English often come from Latin, where it's completely different. It means mother or womb. So matrix, for example, that comes from the Latin. Nothing to do with the Greek word mat. Okay, so finite automata. So it's a kind of an intimidating word because it's Greek, but it just really just means a machine. And in the old days, an automaton was some kind of wind-up toy or something like that. Anything that would sort of move on its own in an interesting way would be called an automaton. Now, we're going to look at finite automata, which means that automata is just plural for automaton. We're going to look at finite automata, which mean that they have a finite amount of memory attached to them. They are the theoretical counterpart of any machine that has only a finite amount of storage in it. And that is actually every machine. A computer only has a finite amount of memory in it. So mathematically it's best modeled, it's most honestly modeled by a finite automaton. Okay? But at some point computers have so much memory that we're better off thinking of them as being something else. Okay? But digital circuits, small digital circuits, just have a finite number of flip-flops in them, and they are very, very properly modeled by a finite automata, especially deterministic finite automata. We're going to start with non-deterministic finite automata, and I'm going to look first, and mostly, we're going to look at automata that only deal with input. So they will be language recognition machines. Each of our automata will either recognize if we can think of it as a thing that we can feed a string to, a finite sequence, and it will either recognize that sequence or it will not recognize that sequence. So each of our finite recognizers will represent be a way of representing a language. Okay? And what we're going to prove over the next couple of lectures is that the languages that we can describe using finite automata are exactly the regular languages. Okay? So that's a really interesting result and quite useful. And it shows that regular languages are actually kind of a limited thing because they um, they require, well, they we can't use them to describe languages that require an infinite amount of memory to recognize, or an unbounded amount of memory to recognize. Okay, so here's the plan. We're going to define a kind of finite automaton called a finite recognizer. Uh, we're going to see that that given a regular expression, we can produce an equivalent non-deterministic finite recognizer, and that will show that every regular language can be described by a non-deterministic finite recognizer. Um, we will look at how to take a non-deterministic finite recognizer, and these are often much easier to build. We can, using such a thing, we can create a deterministic finite recognizer. That's a construction called the subset construction. And we're going to see that given a non-deterministic finite recognizer, we can actually create a regular expression. And so this will complete the circle and show that if I have a regular expression, I can turn it into an automaton. If I have a finite recognizer, if I have a finite recognizer, I can turn it into a regular expression that, that's equivalent. And altogether, this shows that that the languages we can describe with finite automata are exactly the ones we can describe with regular expressions, and those are the regular languages. Okay, so we'll end up with 3 or 4 formalisms that all can be used to describe the same set of languages, and they have their advantages and their disadvantages. It says here 3, but there's actually 4. Okay, so one is regular expressions. We've seen that. The second one we're going to look at is non-deterministic finite recognizers. We're going to look at deterministic finite recognizers, and I'm also going to describe something that I call REFRs, regular expression finite recognizers, and that's a kind of convenient mixture of finite recognizers with regular language with regular expressions, and it makes a kind of nice bridge between the two theories. Okay.